This demonstration will consider the multi-step mechanical simulation of a rotor and shaft components of an electric motor. The demonstration follows these steps. An analyst receives a CAD assembly and idealizes the pertinent geometry for a plane strain analysis of the rotating components of the electric motor. Meshing considerations for a cyclic symmetric sector with local refinements come next. That is followed by the definition of multiple steps in the solution, including press-fit assembly of the rotor onto the shaft, the addition of meshes at specific analysis steps, the application of an operating temperature and an operating rotating speed. Basic post-processing of results such as displacements, temperatures, and contacts are highlighted as part of the review of the multi-step nature of the model. User-defined results such as stress margins computed with temperature-dependent yield strengths are performed with result probes. The demonstration finishes with a durability strength assessment using a wizard interface that steps users through the setup, solution, and results evaluation process. Demonstration is going to cover an analysis of an electric motor. This assembly that we have here shows the electric motor and a transmission housing and case along with a bracket, and really we are going to be focusing on the see-through point of view. We're going to be looking at the analysis in terms of the rotor shaft and the rotor itself, along with the magnets that are inserted into the rotor. And to do that first, we're going to create an idealized part for the analyst to modify the geometry. This is considered the design geometry that the analyst wouldn't have access to editing. We're going to make simplifications to do like cyclic symmetry and also plane strain as the analysis definition. So I'm going to go first create an idealized part. Look into my work part location, and I'm going to put my simulation content in this folder. Go ahead and give that a name, say OK. And essentially an idealized part is an assembly on top of the master part. So that's read-only by the analyst, but from the analyst point of view, I'm able to modify the content in the idealized part. So you see kind of an assembly relationship from the master to the idealized part. And being in a part file, I can do all kinds of CAD operations. So the first thing I'm going to do is link certain bodies that are of interest. And before I do that, maybe I'll hide some of this assembly. I'm going to hide that. And again, I'm focused really on the rotor, and the rotor, the shaft, and some of the magnets. So I'm going to wavelength, pick solid bodies. So solid body, I'm going to pick the shaft, I'm going to pick the rotor, and I also want to pick two of these magnets. So I'm going to produce a sector model, a 90-degree sector model in the positive XZ plane. Go ahead and say OK here. I can hide my assembly, and then this is going to be the solid bodies that I'm going to start working with. So now I'm just going to create some datum planes in order to get my sector and planar face of interest for my plane strain meshes. So go ahead and create my first datum plane as a bisector. So I'm going to pick, say, any of these planar faces is fine. Just somewhere that's going to be in the middle is all I need. And then I'll say apply to that. And then I want to pick another two more. So I'll say by point and direction. And for the center point, and I want to cut along the B plane. So apply that. Same point along the X plane. They apply there. So now that I have my three planes, I can start trimming these bodies. So in order to trim, I'm actually going to go over into modeling. Change my display of my edges. to invisible for the hidden edges. And then I have trim body. So I'm going to do trim body 3 times, I believe. So I need to trim the rotor and the shaft relative to these 2 planes, but I have to do it, one at a time. This doesn't take multiple inputs, and I'm actually going to use the opposite side. So I'm going to reverse that direction. They apply there. So that's step 1 of the trims, and repeat that for those 2 bodies again. Pick the horizontal plane, and now I've got my 90-degree sector that I'm interested in. So I'll apply that, and then I do want a planar face that I don't have just yet for the plane strain. So I'm going to trim all these bodies. I'll say select all, and pick this plane, and then good to go. There's also some defeaturing that I want to do. So I want to remove these small surfaces, these notches. So if I set my filter to face, these little notches, I want to get rid of them. I don't need to mesh to that much detail. And I'm going to actually just use an adhesive. I'm going to glue the magnets onto the rotor. So I don't need those features. So I can use delete face. Here, I'm going to use the ability to find related faces. So I have 4 total faces. I need to turn on that heal option to keep this solid body as a solid, and then you see those faces were removed. One other thing I want to do is I know from operating on this is if I hide this body, no, I actually want that body shown. I want to hide the shaft. So this face combination, I don't need this, and then for meshing, I actually want this one edge, these 2 edges. I want these 2 edges to be one, both on the shaft and on the rotor. So I'm gonna do that using replace face. I'm gonna replace this surface with that one, and it's actually going to combine these 2 faces into one. Got one edge there as well. So that's good for my meshing purposes. And then if I just zoom in on this area just to highlight that I do have overlap in the geometry. So this is, the face of the rotor is larger in diameter than the cylindrical face of the the shaft is larger than the face on the rotor. And so in this analysis, I've got this press fit, and I'm building the overlap in the geometry. So I can also have those flush, and I can have offsets defined in my contact and in the solver. If I have overlaps or gaps, I can also have the solver address that by making these flush and then specifying an offset or an interference. So yeah, my geometry is complete at this point. So now I'll go ahead and save that. Hit OK to this. Now I'm going to go back into pre-post. I'm going to create a new FEM for this model. New FEM, and I'm actually going to use the multiphysics environment. I'm going to use the Nastran solution, which is what multiphysics uses. It's using the nonlinear multi-step solver. Solution 401 is what it's called in Nastran terminology, but the UI is a little bit more convenient when you're using plane strain, plane stress, axisymmetric type elements. So go ahead and say OK to this dialog, and I'm going to create polygon geometry for my FEM from those 4 visible bodies. Maybe use the medium polygon resolution, and I can OK this dialog. Oop, I needed to make a change there as well with respect to the 2D solid option. So I'm going to use plane strain. So I'm going to need this 2D solid option, and choosing the ZX plane with the Z-axis as the revolve axis. But notice my model has its revolve axis defined in the direction. So what I need to do first is create a cylindrical coordinate system, and I'm going to do that by specifying, say, the origin, the z-axis, and the x-axis. So here the origin, I choose there. The z-axis is actually the y direction. I can pick a polygon face as well, so perpendicular to that face. Pick a polygon edge for my radial direction, and so I got R theta Z, looks good, and maybe I'll just change the name of this coordinate system to be cylindrical. So then in the next task, maybe I'll start assigning or setting up the model with mesh collectors and physical properties and materials. So I'm going to do that through the mesh collector command, and find collectors for different topologies, different element types. So for 2D, I can have shells, plane stress, plane strain, and in the property, you really just assign a material. So I'm gonna create a different collector for each of my components: the shaft, the rotor, and the magnet. And in here, I really am assigning a material. So I'll call this shaft again. And if I have this set to inherited, the material would be inherited from the assignment on the solid body. I can assign materials to the CAD solid bodies, and then they would inherit that material in the FE meshes related to those bodies. I'm actually going to use a material library that I've created. So I've got default out of the box material libraries. I have my own here that I'm going to use, and it is library 1 in my collection, and I want to use aluminum for this, and I'll say OK to this and OK, and that gives me a mesh collector. And change display properties. So maybe I'll just change the color from the default to something different, and say OK here. My intent is, this surface is going to be used by that mesh collector. And before I do any meshing, I'm going to define a mesh control. So we have a whole set of mesh controls here. You see, I can define number of elements on edge or size on edge. I can do size on faces. Mapped holes would be like number of elements around a hole, and then options for the layers into the face, away from the hole. And then here I'm going to use the weld row on the two edges at the press fit. So I'm going to pick the shaft edge, the rotor edge, and the two faces that they are related to. And on each side of these edges, I'm going to get elements that are 0.4 millimeters away from the edge, but I'm going to get 2 elements through those layers. I'll have like 4 rows of elements that span this boundary, and the total width of those 4 elements is going to be like 0.8. So I'll add that. And say OK here. So that gives me my my first mesh control. Let me generate a mesh. So here, I open up my 2D mesh dialog. I can pick bodies, faces, and it can even be recipe based to identify bodies or faces. Pick that one, like 0.5 here, and then well, let me make that 1 just to show some kind of transition, because this is 0.4 on that size. And then I've got options to use the paver or subdivision, just different methods to try to control the mesh. I'm going to have minimize triangles, so trying to generate as many quads as possible, and using my shaft mesh collector. So I'll say OK here. This is actually going to produce one mesh, but it's got 2 segments. So it has the primary mesh, so to speak, for everything that is not related to the weld row. So if I zoom in, you can see the 2 layers of elements away from that edge into the face. That is the weld row. And then I have the ability to, if this was actually weld material, I could change that material and physical properties by dragging this into a different mesh collector. But I'm really just doing this for a mesh refinement of the material that's the same as the shaft. And I can do the same thing here for the 2D mesh on this, and I can create a new collector, and that mesh collector is going to need a physical property table. I'll just create a new one, I'll call this rotor and use that same material. Say OK. I'm going to call this rotor as well. OK. Yeah, and I don't think I touched on this yet, but I do have a whole list of elements, linear triangles, parabolic triangles, tension only, plane strain, and I'm using the plane strain parabolic quad. So plane strain parabolic quad, and I'll OK here. Then I've got that mesh as well. So maybe I should have edited that element size from 1 to 0.5 just to get a little bit more detailed capturing of the geometry. Also, if I look in this region, I can pave this edge here. So I'll edit this and pick that definition, and then for its edge, I'll add that edge in there as well. I can update the map. You can see I've got some layering, that as much as it can do given the tight space that we have there. So got some refinement going on there, but there was one step that I already forgot with respect to my mesh controls. But I can always go back and add mesh controls and update my mesh. And that is, for cyclic symmetry, I want to match the mesh on my cut planes. So I want to match edges. We have options to face match, edge match. You can do this in different contexts, so a general context or a symmetry context. And here I have a cylindrical symmetry context, and I want to do it with respect to that coordinate system. Here I can specify an angle from my source geometry to my target geometry. So I have a 90-degree angle here. This is already populated based on dialog memory where I did it in the past. So now I need to pick my source edges, and it's the edges on the independent side of my cyclic symmetry. And then I'll go ahead and say OK to this. And then my mesh will need to update. So let me turn on the 2D meshes, update those. Now I should have equal spacing, along this edge relative to that one, and same for the two moving down. And what I'm going to do is when I define my simulation in the analysis, I'm going to couple those nodes on the independent side to the nodes on the dependent side to force my cyclic symmetry. The next thing I want to do is actually mesh the magnets. And before I do that, I'll just create another mesh collector as plane strain. I'll call this magnet. And I'm going to use a different material for the magnets. Again, it's going to be in that user-defined library. And it is this guy here, neodymium. OK. And OK. Right, so I've got another mesh collector. I'll edit the display of this, make it, let it, give some differentiation from the others. 2D mesh on these. This geometry is all independent of one another. So at the boundary here, I will get, I won't get a congruent mesh, and that's OK. That's kind of what I want. I'm going to even kind of try to emphasize that with an element size of 1. Collector here is going to be the magnet. So just say OK here. Now you see differences between the mesh on the magnet relative to the rotor. What I'm going to do is to make that connection in the simulation. I'm going to use edge-to-edge glue, like an adhesive, gluing the magnet elements to the rotor elements. So one last step that I need to do in the FEM, and that is to assign this to my mesh. So I can do that on the Nodes and Elements tab. Have assign nodal coordinate system. And I'm going to assign it to the geometry. So anything that I assign to the geometry will inherit, on the meshes related to those geometries. So I can pick the bodies, and that finds the faces. I can say select all to get all 4 bodies, and pick my Cartesian, cylindrical, or spherical coordinate system. In this case, it's my existing cylindrical coordinate system. And that's going to apply it to all the nodes as the reference coordinate system for Nastran and the displacement coordinate system. So I'll say OK to this. And at this point, I believe I am done editing the FEM. So I'll save this. And then we'll move on to creating the sim. Okay, so now I can create a new sim. I'm going to do that from the navigator. I tend to drive the product a lot from the navigator. So I'll say new simulation, and it's going to be a multiphysics simulation. Give it that name, and we'll say OK here. And it's going to be a multi-step nonlinear analysis using, like I said before, Simcenter Nastran solution 401. So I'll call this multi-step. Already got some options from the FEM kind of inherited. We'll go ahead and create this solution, and it's got some options that I will maybe come back to. But I might as well go ahead and edit my output request, since I'm going to have to do that anyway. I can preview the output that it already has selected by default. It's got accelerations and velocities and displacements, stresses. So I don't need acceleration, so I can go here, turn that off. I don't need velocity. I can turn that off, the output request. What I do want is, like applied load. I'm going to have a rotation load, so I can see the actual forces that would generate from that rotation load. I'm going to have contact in this model, so I want to enable those results. I want to see the separation distance and my contact status as well. I'm also going to have an interest in maybe looking at strain. And we have the ability to output elastic strain, total strain, and thermal strain. In this case, if I only have a linear material, so I'm just going to output the total strain, and then the thermal strain. I do have a temperature-dependent material, and I could output that, but really the strain here from a thermal point of view is it's expanding freely, so there's free expansion, and thermal strain is going to be essentially zero anyway, so I'm not going to recover that. I also have the need for or an option for glue results. And so for my adhesive between the magnet and the rotor, I'm gonna use glue. So I'm gonna output those results. And if I preview this here, make sure I get everything. I've got my contact, glue, displacements, applied loads, reaction forces, stress and strain. But what I don't have, I also wanted to request my temperature loads. So this is output temperature in Nastran terminology. So I'll say OK to that, and we go back in there, make sure one more time with the preview. And it's got OTemp. Yes. OK, so I'll close that and say OK here. And then OK again from the main dialog. And then this is asking me to create my first step. My first step is going to be just a thermal load applied to the assembly to address the press fit. I'm going to heat up the rotor, and then I'm going to cool down the shaft. So I'm calling that thermal assembly. And that's going to be my first step. I'll create that, and then I can say, what is the end time? Everything is kind of sequenced in a quasi-static kind of time domain. Of output requests. So I'll say 2. I just want to split this into 2 steps. My output request is going to be at the requested increments. I can just do it at the end time or all times. And then I'll say OK here. So I've got my first step defined. And I'm going to have 3 more steps. I'm going to have a thermal assembly step that's going to, like I said, heat up the rotor and cool down to the shaft to open up this gap. And then I'm going to find another step. So let me just create another step as ambient assembly. So I'm going to cool down, or I'm going to let the model go to ambient in this step, and it's going to form the contact between the rotor and the shaft. End time is going to be at 2. I'm going to have 4 increments that so I'm going to step this through in 4 steps and say okay. So that's good to start. I'm going to have 2 more steps as well. But now let's, before we get into the actual loads, let me go back to maybe some of the content we will define at the global level, primarily the constraints. So I'm going to turn off the mesh controls and the mesh display and create a new constraint here as a fixed constraint. I'm going to fix the vertex so I can fix geometry and nodes and whatnot. So I'm going to fix this vertex on the axis. Fixed axis. And then this will apply to the entire solution as long as I don't override my constraints in the subcases. I also want to I'll cancel this because I want to define a user-defined constraint. This is going to be fixed theta on the independent side of my connection. So here I'm picking polygon edges, so there and there, and I want to fix the rotational degree of freedom, and I'll say OK to that. And then I also want to create my cyclic symmetry couple. So I'm going to do a new constraint as a static couple. And in this case, I'm picking geometry to define my coupling. It's asking me to pick an independent seed object. It's asking me to pick a point on the independent side. So I'll pick that point there. And then pick the equivalent point on the dependent side. So I go there. I need to specify my cylindrical context. And now it's going to, kind of form the rotation angle and the radial displacement even from this point to there. I try to match nodes within this tolerance from the nodes on the independent side to the nodes on the deep. If this was a big model, I could limit my candidates for the independent side to just these edges. That would help performance in the evaluation of this, but it's a pretty small model anyway, so it doesn't take a long time. And I want both the radial and the cylindrical directions coupled. Say OK here. And what that gave me was this automatic coupling. I can change the display here to reduce the size of the graphic. And it's drawing a line from the node on the independent side to the equivalent node on the dependent side. So I've got my constraints defined. Another thing that I'm going to need at the global level in terms of this model is an edge-to-edge glue. So you can see I have different options. Cyclic symmetry would be for a solid model where we're coupling faces together. I did that coupling here on edges with the automatic coupling constraint. And the difference there is cyclic symmetry on faces, it doesn't require matched mesh. So on my cut planes, I could have different mesh distributions with cyclic symmetry. And with the automatic coupling that I did, that requires matched meshes. So I'm looking for nodes from the independent side to the dependent side with a search tolerance. So we have surface-to-surface contact and glue. We have edge-to-surface glue, and then edge-to-edge contact and glue. So this is one definition, and I can flip the switch between contact or glue. So I'll use this, but we also have dedicated contact and glue definitions. So I'll use this to glue I'm going to glue the magnets to the rotors. So I'm going to turn off the rotor right now, and I'm going to use manual pairing, and I'm going to create 2 regions. Brought the rotor back in the display. I'll go ahead and create the magnet region first. Magnet. All this magnet glue. Pick these 4 edges, and you can see I can even for the contact parameters I can define an offset here. So if I want to introduce an interference or create a gap, I can do that. I'll say OK here, and the target region on the I want to display the rotor and not the magnets. Call this rotor glue, and I'll pick these edges. Dialog. Okay. And I can also offset this region, so the regions can be offset independently. Then search distances, I can go in a negative sense for my minimum 0.1. In a positive sense, I can give friction coefficient. And actually, so this is like setting it up for glue. So, I mean for contact. But in this case, my type is going to be glue. So when I change to glue, it has the glue definitions here, and independent of the contact items, but no friction because it's glue. But you do have a search tolerance that you're interested in, and I will say OK to this. All right, so I've got my surface or edge-to-edge glue at the global level. Now, one thing I do want to do next is I'll focus on the loads, and then I'll come back to the magnets and when I want to introduce those into the analysis. Okay, so now I want to focus on definition of loads in the first two steps, the thermal assembly and the ambient assembly. And really, it's just going to be a temperature load for each one. So I'm going to first make this step active, and for temperatures, it's a temperature load, so I need a load container in this subcase. And then for temperatures, we always contain temperatures in temperature sets. You see here the default temperature set, and I actually can change this one, its name. I'm going to call this ambient. And if I look at ambient, how it's defined, so this is 20 degrees Celsius as an initial temperature for the solution. So I'll say OK here. And what I can do is use that in my ambient step as well by defining nothing in that step. But for my thermal step, I do need a new temperature set. I'll call this thermal assembly. And I don't really need a temperature here for the default because I'm going to assign temperatures to all the faces in my model. But this would be a default temperature for when a temperature isn't assigned to a mesh or geometry. Say OK here. Turn on the display of my geometry. And then in those, in that load, what I want to do is create a new temperature for the shaft. So I'll call this shaft cold. I'll pick the surface, and then I'm actually going to apply a temperature of minus 25 Celsius to the shaft. I'll apply that, and then I'm going to apply a temperature to the rotor that is hot. And that temperature is going to be 100 Celsius. I'm going to leave the magnets alone. So the magnets actually aren't going to be part of this step, so we'll see that in a bit. So I'm going to only have the mesh on the shaft and the rotor at this point in the solution. They both have temperatures defined. I can do a contour plot now of these. Say plot contour. There we go. If I go to the results tab, they're actually showing this as spheres, so I can do a contour plot. And you can see, okay, I've got 100 degrees on the rotor, 25 degrees on the shaft. Okay, so then I'll return to model, and I'm good with that step. That's the only load I'm going to have in that step, just to open up the gap between the rotor and the shaft. So then I'm going to the step active, and actually I don't need to do anything here. And what will happen is the global loads and the global constraints are always applied when you have nothing defined. So in this case, the temperature set for the ambient assembly step is going to be the one defined at global. So I'm going to go from a hot rotor from this step and a cold shaft. I'm going to go to ambient in the second step. create another step. So new step, and this step is going to be called operating operating temperature. And I'm just going to apply a temperature load that's going to vary across the geometry. So I say create this step and make active. Here is going to be 3. It's my third step. I'm going to have 4 steps here. And then my output request, I'm going to do it at all times. And we'll see how that impacts the results that we recover. Okay, so before I actually generate my temperature set and the temperature load, I'm actually going to have to import a temperature field in the interest of time. So I'm going to call this operating temperature, and default temperature 20 again. Let's say OK here. And we have the concept of spatial fields to apply spatial variations to loads and constraints. And I've got a spatial field already stored. This is for the FEM, this is for the Sim. I'm going to import a field from a text file. Text file is in my work part location in this folder. Here it is, right there. And so it's a temperature field that depends on radial dimension. So I'll say OK here. And then we'll see if I rotate this around, I can turn on the display of that field, operating temperature, and there it is, the points highlighted here. And it just so happens that it's on the same axis. But I could change the coordinate system that it's referencing. If I look at the definition here, the independent domain has a coordinate system reference picked there. I'm going to leave that since it's on the same axis and in parallel to my coordinate system on my geometry. It has a field data source, so it says it's related to that field file, and if that field file were to change, I would have the opportunity to update it. Cancel this, but no, I want to actually look at the definition as well. And you can see, I've got a radial coordinate value and then a temperature value. And this could be r theta z, it can be Cartesian, it can be time dependent as well. So I'm going to OK all that. And now I'm going to create a load that is using that field. So OK, in that temperature set, I'll create a new temperature that is operating to pick all of my faces here. So the magnet and the rotor and the shaft, and then going to select an existing field. So I can create a new one, if I want a new formula, new table of data, and so on, but I have that existing field. I'm going to pick that one and say OK and OK, and then do a contour plot of these temperatures. Do that, and you can kind of see the variation that I have going from 50 degrees at the center of the shaft to a peak of 80 somewhere in the middle here, and then falling back down again. So just a little bit of variation, nothing too fancy there. Okay, so then one thing I did mention is I wanted to assemble just the rotor and the shaft together, but then when I get done with the assembly, I want to introduce the magnets into this model. So we do have an element birth and death capability in the solver. And to do that, I'm going to define a new simulation object at the global step, and it's called element add or remove. Here I'm going to pick, I can pick the geometry, the mesh. So I'm going to pick the mesh, turn that on. I pick my magnet mesh, and then I'm going to specify at the time point of 2.01, so early on in this operating temperature step that's spanning from 2 to 3 seconds, the magnets are going to be introduced into the model. and I want to add them as stress or strain free. That's all I need to do at this point to introduce those. And then when they are introduced, they'll be connected to the rotor by the edge-to-edge glue. Okay, so then hide that display. And then for simplicity, for the definition of my last step, I'm going to clone the one I have here, and it's going to use the same operating temperature. I'm going to clone just one step and say OK. Rename this to be operating load, operating speed. I'm adding a rotation load, so you can see it's got the operating temperature in there, and I need to create, or I need to make this active, create a new load as a rotation. So it's going to be a whole model rotation. Everything in the model is going to rotate. I don't need to select any objects. The coordinate system, I'm going to leave that as global, but then I'm going to say for my point, I'm going to pick a point as that location on the shaft, the existing point, related to the coordinate system, and then, oops, I think I maybe did that backwards. So what I want to do is for the vector, I will pick, say, a polygon face, pick that face, and I get the vector, and then for the point, pick that point there. And then for my rotation, it's going to be 2,000 RPM. And change the units to RPM and say OK here. So I got my rotation and my temperatures. And I think I have everything defined. Is that right? No, I don't. I don't have everything defined. I do need to define contact. And I didn't define contact yet. I want to introduce my contact in the ambient assembly step. So I'm going to make this active. I'm going to create a new simulation object container. And in here, I'm going to create edge-to-edge contact. I'll just manually do this. Manually, I'm going to create two regions. I'll create a region for the rotor contact, and pick my polygon edge that's on the outside. Again, so I can say an offset. I can specify offsets in my regions, or have it in the geometry. I can have it in both. I'm going to say OK here with no additional offset. I create a second region as, I think I picked the wrong edge there. I picked the shaft, so I'll call this shaft. I'll pick that same edge. I picked the right edge. I'm picking the outer edge here for the shaft. Search distances, I'm going to do, minus 0.1 to 0.1. Include friction, and I want to go back to that rotor to make sure I picked the wrong edge for the rotor. So I'll deselect that and pick there. And then say OK here. And then I also just want to show you one last option in terms of the contact and initial penetration. There's a whole concept here of how to evaluate the initial penetration or the gap. And by default, we calculate the initial penetration from the geometry, and I'm going to leave it at that. But I can also say, well, if I do have a gap, just ignore it. If I do have penetrations, I can set them to 0, and I can set gaps and penetrations to 0. And then if I do that, I can specify a constant gap value, and that gap value can be positive or negative. So I can have interference. So we have additional options here, even in the contact setup in the solver, to address the whole interference topic. So you can do it in the geometry, you can do it in the regions, and in the definition of the contact parameters here as well. So I'm going to cancel that. and then say OK. So I've got my contact here for the ambient step. Now I need to add that into the operating temperature and the operating speed. So when you have simulation object there, and then I can drag and drop this contact into that step, and I do the same thing, new simulation object container, and drag and drop this edge-to-edge contact into the operating speed. So I could have cloned, when I cloned, if I'd already had the contact defined, that would have cloned it, at least for the operating speed step relative to the operating temperature step. So now I think I have everything ready, and I will do a model setup check. So run model setup check, tells me I do have an error. Operating speed occurs at a time before the end. Yeah, and I didn't modify that end time. So I did to modify this and make this end time is 4 instead of the previous time of 3. And so that's the only modification, the only error I had. And at this point, I can go ahead and solve. I'll do that. And we will bring up the solution monitor. So instead of watching the solve on the solution monitor, I decided to skip forward, and the solve is now complete. So I can go and load the results. Take a look at what we have. First start with the displacements. So take a look at the displacements at the first solution step. And I guess notice that we don't have results on our magnet. That's because the magnet they've not been introduced in the solution yet. And if I zoom in on the interference of the rotor with the shaft, and you can see it's already starting to open up. I look to the next step, and it's opened more. And if I look at the temperatures at this step, hit apply, you'll see I've got the 100 degrees Celsius for the rotor and the -25 for the shaft. So that's all kind of as expected. And then I'll just cancel out of here and step through into the next step, which would be the ambient. So I'm going to go traverse the ambient, and the colors on the screen won't change, but the numbers on the color bar are changing. They're getting closer to 20 degrees Celsius. So now I'm at the end time of 20 degrees Celsius, and then at this point, I can change my results again at the contact pressures. So we've got contact was introduced in this ambient subcase, ambient assembly case. So I'll say apply here. You can see the nature of the contact pressures on the edge-to-edge contact. I can look at status as well. Most of the contact is closed. We see some open conditions on the end. So 0 is open, 1 would be sliding, and 2 is closed in this case. If we go back to, say, our temperatures, because the next step is going to be the operating temperature, set that result to temperature again, and then we'll step into the introduction of the magnet. So notice I'm at time 2.00. The next time step is going to be 2.01, and this is called increment 1. So this is the point right before the magnets are being introduced, and then I go to 2.01. The magnets are now in the model, and temperature is starting to change, but it's really not. Change the results again. Take a look at our strain. Should have complete 0 strain throughout the magnets because we're introducing it at 0 strain. But I mean, we also have practically 0 strain on the rotor as well. So maybe it's going to be 0 anyway. So if I go and change my result to temperatures, also change it from to the end of the step, and say, okay, here, now we get the distribution that we saw on the load from the spatial field of temperatures varying radially. And again, we can change results, look at, say, strains or stresses. So go ahead and look at strains, and see some differences there in terms of discontinuities because these meshes aren't connected. It's the same material here, but I don't have connected meshes. It's connected through contact, so that's why that's discontinuous. And we have discont here again, different meshes. I can even maybe emphasize that by turning on the element borders. I've got different meshes for the magnet and the rotor in terms of distribution and then also materials. Looking at the magnets now, I can also look at the glue results. So go ahead and change that to, say, a glue force, apply, and then we get the forces that are being invoked due to the adhesive. That's the force that's keeping the magnet in place, connected to the rotor. Okay. Just go to stress and say average. So turn on averaging, and then we can step through from the final. This is the peak temperature load, and then we have the last subcase, which is adding the rotation, so increasing the rotational velocity. And the contours pretty much aren't changing, but again, the numbers on the color bar were changing as well. So now I want to create a result probe that will compute a stress margin. So since I've already got stress here displayed, I'm going to end up creating a new result variable. A result variable would be an input to a user-defined computation. I want to create a computation based on stress, and so I do that with result variables and result probes. So I'll create this new result variable. I'm going to call it stress VM for von Mises average, and say OK here. And I also want to base this on the temperature of the model. So I'm going to change my result to temperature and say OK here, and create a second result variable as well. And I'll call it OTemp for temperature. OK here. And then maybe just for awareness, show you, the results variables are collected in a result variable manager, and I can create new result variables independent of post views. But using a post view is a very convenient way to generate a new result variable. So okay, I'm going to return back to the display, and I will next create a result probe, which I can get to it from the ribbon here, or I can do it from a right mouse button off of the solution. So new result probe, and I'm going to call this stress margin. Oops. It's going to be based on stress. And so I'm going to say 1 minus a ratio of stress. So I had stress VM, divide that by a yield function. So we have an out-of-the-box function called yield. Yield will evaluate an element's material, and it'll look for the yield strength of that material. And if it's temperature dependent, it'll use the temperature dependent value for, a given node, its temperature, and that element. Go find me the yield strength of that material at that temperature. So it's a basic stress margin here. If it goes below 1, or if it goes negative, then I will have stress that exceeds yield. I'm going to do that across the entire model. I can envelope. There's combine across iterations where I can get a maximum, minimum. Just do just compute a value at every step as a possibility, and instead of it's a unitless quantity, it picks the first unitless quantity in the list as an absorbed radiation, but I'm going to call this failure index. And then when I say OK here, it's going to compute that value and generate a contour plot. So it's computing the values, and then this is at the first step, which is kind of meaningless for me, but maybe I'll do it at the ambient position where the press fit is finally initiated, and go ahead and say OK to that. So reverse the color bar, invert the color bar here. So now problem areas are showing up, in red, and the safe zones are showing up. So the corners here, I guess, are where the maximums are located. You see, the evaluation doesn't occur at this step on magnets again because the magnets weren't at that step. So I'm at 0.28. So I'm still okay, but getting close to maybe exceeding yield. If I go and edit the results one more time, I can go to the operating speed and the final increment. It's okay here. Are computed their yield, and I'm getting much closer to 0 as well. But maybe that's a singular region, and I would want to possibly define a subset of my model to consider. So I can do that, with groups or selection recipes. So what I'm going to do next is create a selection recipe that is going to be based on a proximity. So I'm going to create a proximity-based selection recipe, and it's going to look for nodes or elements near this vicinity. In general, we have selection recipes as bounding volumes. I can pick any of these objects that are within a volume. These are going to be like cylinders, spheres, cubes, or even arbitrary volumes created by polygon geometry or a mesh. I can also pick, faces, bodies, points by attribute, so like by name or color, or attribute value, node and element by label. And here I'm going to use proximity. I'm going to call this proximity nodes, and it's going to be my entire model. I'm going to pick a point to create a point, don't I? Let me cancel out of here. I'll create my point, and pick a point on my model. So right there, the midpoint of that edge is going to be my focus for my selection recipe. So new selection recipe and proximity. I'll call that again proximity nodes. But it's the entire model, and as soon as I can get there, pick that point, and then my tolerance. Its radius is 18, so maybe I'll do 15 or 10. Do 15 first, and show result. I've got to show my mesh, undo, turn, show result. It's not showing it, right? I'm going to say OK to this, and then show contents, select contents. Why is it not picking them? Cancel. Clone this guy. Can I clone it and say node? There we go. So what I messed up in my selection. Instead of picking point, I should have picked node, and I kind of confused myself on the selection step. So yeah, 15 is a little big, so maybe I'll say 10. I can delete the source and call this proximity nodes again. So now I'm back where I really want to be, and again, select contents. So that's all making sense once again. And then I perhaps evaluate my result probe. Once again, I'll generate, it's first going to generate the display based on the first step. I can set the result again, to maybe the operating temperature at its temperature without the rotation. So I get some data there, and then on my post view, I can look at a subset of my model, so show only that result, and then you see the color bar adjusted according to the data that's in the display. Okay, so from here, I'm going to move on to a little demo on durability. So I'm going to create a durability solution process on the simulation using my results from the multiple step solution. And I can do this through new solution process. There's durability, and then there's specialist durability wizard and specialist durability. I'm going to use the wizard. And then the wizard, its capability can expand into the specialist durability. The wizard's a very convenient way to step you through this process. So I'm going to do, call this strength assessment and hit enter. And then I just follow the steps in the dialog. So next would be definition of the load. So I'm going to obtain, results from my solution, and I'm going to define a transient event. So I'm going to grab results not from the first subcase, because that was just expanding and preparing the model for the preload. So opening up the preload interference so that we can get closure at that next step. And then we have our operating loads. So I'm going to consider those and then go to the next step. I'm going to use, we have strength analysis, stress life, strain life. I'm going to use the default stress life, and we have locations. I'll stick with that default. We have Goodman here as mean stress correction along with Soderberg. So I'll use Goodman. And then for the strength safety factor, we have the yield strength and max stress, tension, compression. So looking at stress in tension and compression is the option I'll use. And then I will step to the next option. And then I could inherit the material properties from the model. I don't have the proper durability quantities, material properties, so I'm going to use this estimate option. I'm really going to be focused not so much on the magnet material, but the aluminum of the rotor and the shaft. And so I'm going to base this off of a typical cast alloy aluminum. In my material, I have a yield of 383 megapascals. I can then preview this material. So I'm going to hit enter here. And it's going to create a new material called aluminum cast alloy UTS 383. It's going to create that in the model and use that for the elements that I use in my durability computation. So here I'm going to create a plot of stress amplitude and number of cycles. So this is the stress life curve, and that looks good. And I'm going to take a step, and here is where I can decide what I want to compute or where I want to compute the results. And in this case, I'm going to do the location as the nodes instead of the entire model. I'm going to select elements, and I can use my selection recipe. So I have these proximity nodes. I can put that in the selected list and then say next here. At this point, I can solve. So it's going to do a quick solve, and another window this popped up, so it completed successfully, looking at all of my steps that I had selected from the ambient assembly subcase through the operating speed subcase. I can start post-processing. So I can look at, say, max stress. It's the envelope max stress in this region. And again, this is going to start resetting the display for me. So you're going to find me moving the display around, and it's also displaying just elements on the boundary. So look at mean stress, huge stress, so the safety factors. So static safety factor. Here I can apply a durability post view template. So it's going to change the color bar for me. Pretty much if it is red, it's an indicator that it's less than one, or orange would be less than one. So it's a less than one is failing here. So I'm in the yellow zone. If I was green, I'd be really good, but I'm in yellow, so I'm closer to 2 than 1,000 being yellow. I can annotate the worst value here, 1.78, and um, go ahead and finish that. So the last thing I want to show is that I can take this durability uh, event and I can edit it in the wizard, or I can edit in the specialist durability application. And here we have a lot more capability in terms of what we can modify. I can go into, say, the Goodman. I can go into the mean stress correction, and if I want to use something other than Goodman, this Goodman original, I can create a new simulation object and go into different settings or different options here. So it's this whole specialist application opens up a whole lot of durability options, in terms of life prediction and strength analysis. Just wanted to bring up some of these dialogues to highlight the additional capability. And there's also this idea of analysis templates. The user can create an analysis template. So once the expert in your department sets up calculations for durability based on how you want to do them, those can be stored as a template, and then those templates can be deployed across your departments for your users to apply, even though they don't have a full understanding of the theory behind the computations. That's it. That's the end of the demo, and thank you for your attention.